Okay, in this video we're going to start exploring how can we find these zeros, because in the previous videos we've actually been telling you one of the zeros or one of the factors. Now we're going to start actually figuring out how to find those on our own. First off, recall that a polynomial of degree n, like an x to the fifth would be a fifth degree and x to the sixth would be a sixth degree, can have at most n real zeros. If it's an x to the fifth, it can't have more than 5 zeros. Real zeros can be either rational or irrational, because real numbers, if you remember the group of real numbers are either rational or they're one or the other. Rational zeros are those that can be written in the form of a fraction or ratio, which is again why we call them rational. Okay, now let's talk about the rational zero theorem. Here we go. The rational zero theorem can be used to determine all the possible rational. Now, you've got to be careful because, reminder, that these zeros can be rational or irrational. This theorem will only give you the possible rational zeros. So, all the possible rational zeros of a polynomial function. And here's the actual theorem. If f of x equals your polynomial function, has integer coefficients, which means that's positive and negative whole number coefficients, then every rational zero of the function has the following form: p over q, to where p is going to be factors of the constant term. And reminder that the constant term is that last term, that plus 3, plus 5, minus 6. So factors of the constant term x of 0. And q will be factors of the leading coefficient, or this coefficient, a sub n. Okay, now let's actually try out this theorem and show you what it means. Number one says list all the possible rational zeros of each function. And for what we just said, all the possible rational zeros, not every one of them, but all the possible ones, will be of this form: p over q, to where p is all the factors of the constant term, q is all the factors of the leading coefficient. So here's what we're going to do. And number one, identify your constant term, which in this case is 2. There, 2 is your constant term. Your leading coefficient is 1. So what you're going to do, all the possible rational roots, we'll call them PRRs. All those possible rational roots are of this form: p over q, where p is all the factors of your constant term. So in this case, a positive or a negative 2 is a factor of 2, and a positive and negative 1. That's all the factors of your constant term. And you can put a comma there, however you need to do it. But you're going to list all the factors of your constant term over all the factors of your leading coefficient, which are positive and negative 1. Now, what we're going to do is now find every combination of these terms over these terms. And what I mean by that, let's start out with 2. And let's do 2 over 1, which would be positive and negative 2. We're done with this one. And then move on and do positive negative 1 over 1, which would be positive or negative 1. And that's it. Positive 2, negative 2, positive 1, negative 1 are all the possible rational roots of this function. Let's do another one. All the possible rational roots, again, we'll call them PRRs, are all the factors of 18 over all the factors of 1. So we're going to list all the factors of 18. We'll start with 1 and just start seeing if numbers will work. Possible rational roots are positive, negative 1. And these, again, are the factors of 18. 2 is a factor of 18. 3 is a factor of 18. 4 is not. 5 is not. 6 is. 9 is. And 18. That's all the factors of 18, positive and negative, over a positive or negative 1, which is the only factor of 1. So all of your possible rational roots is every combination of tops with bottoms. So you have 1 over 1, which is a positive negative 1. And you have to consider both of these scenarios. Positive 1 over positive 1 is 1. Negative 1 over positive 1 is negative 1. So that includes both of them there. Positive and negative 2 over 1, which would be a positive or negative 2. Positive negative 3 over 1 would be a positive or a negative 3. A positive negative 6 over 1 would be a positive or negative 6. And continuing on with our list, these are all the possible rational roots of this theorem, or excuse me, of this function. Number 3, let's do another one. All the factors of 1 over all the factors of 4 are all of your possible rational roots. The factors of 1 is just positive or negative 1. The factors of 4 are positive negative 1, positive negative 2, or positive and negative 4. So again, we're doing every combination. Let's start with 1 over 1. 1 over 1 is equal to 1, comma. 1 over 2 is positive and negative 1 over 2, which is 1/2, or 1 over 4 would be a positive or a negative 1/4. So those 6 rational numbers are the 6 possible rational roots of this function. Number 4, the possible rational roots are all the factors of 16 over all the factors of 3. The factors of 16 are 1, 2, 4, 8, and 16. The factors of 3 are 1 and 3. So this one we're getting a little bit tougher. So here's your possible rational roots. Let's start with the 1 on bottom. Let's do 1 over 1, which is positive negative 1. Let's do 2 over 1, which is 2. 4 over 1, 8 over 1, and 16 over 1, which will be obviously 4, positive negative 8, and positive or negative 16. We're done with the 1. Now let's move on to the 3. 1 over 3 was a positive or negative 1 over 3, 1/3. 2 over 3, which is a positive or negative 2/3. 4 over 3, which is a positive or a negative 4/3. 8 over 3, which is a positive or negative 8/3. And finally, 16 over 3, which is a positive or a negative 16/3. Now, this one has several. And I'll go ahead and tell you before we start working these problems, this is not a problem that you want to work. This thing has, 10 different possible combinations, but you have plus and minuses for each. So actually 20 possible rational roots there. Number 5, the possible rational roots are all the factors of 12 over all the factors of 6. The factors of 12 are 1, 2, 3, 4, 6, and 12. Over all the factors of 6 are 1, 2, positive negative 3, and 6. Now let's do every combination, and we'll start with over 1. Now these are going to take a while to list. Let's do every one of these over 1. Okay, so we got 1 over 1, 2 over 1, 3 over 1 is 3, 4 over 1, 6 over 1, and positive or negative 12 over 1. We're done with the 1. Let's move on to 2. So you got 1 over 2, positive negative 1 over 2, 2 over 2. Okay, now look at this. 2 over 2. 2 divided by 2 is 1. That one's already listed, so we don't have to list it again. 3 over 2, 4 over 2. 4 over 2 is equal to 2, so we don't have to list it again. 6 over 2 is 3. We don't have to list it again. 12 over 2 is 6. We don't have to list it again, so that's done with 2. Let's move on to 3. You have a positive or negative 1 over 3, positive or negative 2 over 3, 3 over 3, that's going to be 1, so we've already got it listed. You don't have to do it again. Positive or negative 4 over 3, positive or negative 6 over 3. We're here. 6 over 3 is 2. We've already got that listed. And then finally, 12 over 3 is 4. We've got that listed. So we're done with the 3. But our list still goes. Now let's move on to all these top combinations with 6. Positive and negative 1 over 6. 2 over 6 is going to be 1/3, which I believe is already on our list. so we don't have to do that again. 3 over 6 is a half. It's already on our list. We don't have to do it again. 4 over 6 is 2/3. It's already on there. 6 over 6 is 1. And 12 over 6 is 2. So I believe that's every possible rational root, but there are lots for this problem. You'll find out that numbers like 12, 6, or 12, 24, 32, those are some scary numbers when you're finding possible rational roots. So let's do one more. All the factors of 24 over 2. Factors of 24 are a positive or negative 1, 2, 3, you don't have to put a comma, 4, and this is a list. You can put commas in between them if you'd like. 6, 8, 12, and now I've started putting commas. I don't know why. Positive or negative 24. That's all the factors of 24 over all the factors of 2. At least there's only 2 of those. And let's do every combination. We'll start with a 1, and we're going to do every factor on top with a 1. You have 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 8 over 1, 12 over 1, and 24 over 1. We're done with a 1. Now let's move on to 2. 1 over 2, which is a half. 2 over 2 is already listed. That's 1. 3 over 2, that one's not listed yet. Positive, negative 3 over 2. 4 over 2 is listed. 6 over 2 is listed. 8 over 2 is listed. 12 over 2 is listed. And 24 over 2 is listed. So that is all the possible rational roots of this function. But just one more time, a reminder that these are only the possible rational roots. So what we're about to do will only give you the rational roots of these functions. So now how do we actually use that? Here we go. Step number 1. We're going to generate that list. List all the possible rational zeros using this rational zeros theorem. We're going to generate that list. Then, here's the scary part. Step number 2, we're going to test the zeros using synthetic substitution. The same way we've done before. We're going to look for zeros pretty much by plugging them in until we find one that gives us 0. So we're going to search for those zeros. Step number 3, when you find a zero that works, use the remainder. And instead of a remainder, that should say use maybe the leftovers of the function to completely factor the polynomial, then find the zeros. So here we go. Let's actually do this. Notice it says list all the possible rational zeros, then find the actual zeros. On this one, we're not given one of the factors. We're looking for possibly 3 because it's an x to the third, but we're not given any of them. So let's see, can we find all 3 of them? First off, you start by finding all your possible rational roots. That would be all the factors of 8 over all the factors of 1. Let's list them over here so we'll have more room. Positive negative 1, positive negative 2, positive negative 4, and positive negative 8 over all the factors of 1, which is positive negative 1. So our possible rational roots are every combination. Positive or negative 1, positive or negative 2, positive or negative 4, or positive or negative 8. So what we now have is a list of 8 possibilities for roots of this polynomial, rational roots. So how do we find one that works? We start testing. And this is when being a good guesser actually comes into play because you're going to try to guess one that's going to work. There's nothing that we can do but look at our list, and I'm just going to start trying. I'm going to try 4. Because again, 4 is on my list, a positive 4. Let's see if it works. The way we see if it works is, again, synthetic substitution. Is 4 a 0? Bring it down, multiply, add. 28 minus 6 is 22. 88, and I get an 80. So what does that mean? The only way that this can be a 0. Remember that the factor theorem says the only way it can be a 0 is that if f of 4 is equal to 0. We just plugged in 4 by doing our synthetic substitution. When I plug 4 into this, and you can see it right here, I'm going to write it one more time. F of 4 is equal to 80, the remainder. So is that a 0? No, it's not. Let's try another one. Let's try negative 1. So we try negative 1 into 1, 3, negative 6, negative 8. Bring down our 1, multiply by negative 1. Add those two together. Negative 2, negative 6, negative 2 is a negative 8. Negative 1 times negative 8 is a positive 8. Remainder 0. So what does that mean? That means that f of negative 1 is equal to 0. So that means that negative 1 is a root. That means that x plus 1, because again, if this is the root, what goes along with it? What did we just divide by? We divided this by x plus 1. If this is the root, then x plus 1 must have been the factor. So now let's go with that. We took our function, f of x, which was x to the third plus 3x to the second minus 6x minus 8. When I divided the function by x plus 1, I got this, constant x squared, which is x squared plus 2x minus 8. So what can I do now? I finished factoring. Do I have to use this new method? No, because this is now quadratic. As soon as you get to quadratic, use old methods, because all we're doing is we're factoring this stuff out. And to factor out x to the third stuff, our new method is we can use this synthetic division stuff or synthetic substitution. When I factor it out, what I've got left, this is what I get. And once I get to linear factors, guess what? Now I can find my zeros. My zeros of this function, set each of these factors equal to 0, because again, that's what you do in order to find an x-intercept. And your three x-intercepts are negative 1, negative 4, and positive 2. Look at your list. Negative 1, negative 4, and positive 2. All three of those rational roots were on your list. Move on to number 8. Let me zoom in just a little bit. First step is to find all the possible rational roots, and I'm going to list them up here. Actually, we'll list them right here. Possible rational roots. We're going to do all the factors of 20 over all the factors of 1. Factors of 20 are 1, 2, 4, 5, 10, and 20 over positive or negative 1. So we're going to do 1 over 1, 2 over 1, 4 over 1. Instead of rewriting that whole thing again, hopefully we see that those are going to be the possible rational roots. So now what do? We test them till we find one that works. Let me change colors here, and let's pick one randomly to try to test. I'm going to test a positive 2. So synthetic substitution, when I plug 2 in, and do I have to use this method of plugging it in? No, you could do 2 to the third is 8 minus 42 plus 20, which I don't think this is going to work, but we'll try it out. So 1x to the third, 0x to the second, negative 21x, positive 20. Bring down the 1, multiply, gives you 2. Multiply 4, negative 17, times 2 is negative 34. That'd give you negative 14. So what did we just find out? F of 2 is negative 14. So is 2 a 0 of this function? No, it's not. Is x minus 2 a factor of this function? Because a 0 of 2 would go along with a factor of x minus 2. No, it's not. So let's try again and see if we can find one that does work. And you can cross out that positive 2 from your list. Okay, let's try 1. Same list of coefficients, negative 21 and 20. Bring down the 1, multiply, add those two together, multiply, negative 20, multiply, and it gives you 0. So therefore, 1, f of 1 is 0, which means that when I plug in 1 for x, I get 0 for y. So since 1, 0 is on my graph, then that's one of my x-intercepts. So now that I've found that, look what I can now do. My original function was x to the third minus 21x plus 20. I divided it by x minus 1 just now. This is x minus 1. When I divided it by x minus 1, I got this, which is x squared plus x minus 20. So that's my new function. So now what can I do? I can break it down with old methods. 2 sets of parentheses, adds, multiplies would be a positive 5 and a negative 4. So this is my new function. my factored form of my function. So therefore my zeros, which is what I'm now looking for, are x equals 1, which we found to be right here, -5, and +4. Next problem. Now we're looking for at most possibly 4 different zeros. Okay, that's the most it can have. How do I find them? Okay, possible rational roots are all the factors of 18 over all the factors of 1. So all my possible rational roots are 1, 2, 3, 6, 9, and 18. I don't think I've left one out. Over all the factors of 1, which are 1. So you do 1 over 1, 2 over 1, 3 over 1, 6 over 1, 9 over 1, and we all again see that these are my possible rational roots. Let's test one to see if we can find one that works. Again, let me change colors so I can keep track of it. Okay, let's test maybe 2. My coefficients are 1, 3, -7, -27, and -18. Bring it down, multiply, add, multiply, add, multiply, -21, -42, -60, nowhere near. My remainder tells me that f of 2 would be -60. Now think about this. Here's you some more advice for guessing. F of 2, that means the point, that's a point. When I plug in 2, I get -60. So 1 point on your graph. If you were to plug 2, use a t-table and plug 2 into this, it would give you -60. So 2, -60, which is way down, but not that far, somewhere way down here. When you go over to 2, go down to -60, that point's on your graph. You're nowhere near the x-axis. So as I guess, I try to guess, well, maybe that's not very close. Let's try something a little bit further away. But let's try another guess. Let's try maybe -2. So you're pulling or dividing -2, which again, the actual factor that you're dividing by is x plus 2. And you can keep that in mind. This means you're dividing by x plus 2, 1, 3, -7, -27, -18. Bring down 1, multiply, that'd be -9, 18, -9, 18, and 0. So that does work out. So your original function, let's come over here and write it again. Your original function was x to the 4th. Let me move it over so we'll have more room. Okay, there we go. That's my original function. I just took that function and I divided it by x plus 2 right here. And I got this, which is constant x to the 1st, x to the 2nd, x to the 3rd. So that would be x to the 3rd plus x to the 2nd minus 9x minus 9. Now the question is, do I have to do that again? You now have 2 options. You can now take this, okay, this portion, and try to break it down again using the same method. You could do all the factors of 9 over all the factors of 1. And what that would actually do is it would cut out some of your factors. It would take that one off. It would take this one off, and it would take this one off. So you wouldn't have near as many, and you could test some of those. Okay? Or you can use old methods. If you notice that this has now 4 terms you can try, and this is always the best method, try to factor by grouping, because the old methods that we first learned are the quickest methods. So let's see if we can factor this thing by grouping so we don't have to do our whole list stuff again. So we're going to group our first 2. We're going to factor an x squared out of it. You're left with an x and a plus 1. Second group, you're factoring out a -9, and you're left with an x plus 1. So this old method is going to work. Both parentheses have x plus 1s. Bring this x plus 2 down. So we're going to factor the x plus 1 out of both of those, and you're left with an x squared and a minus 9. And again, the old methods. Bring down x plus 2, bring down x plus 1, and now let's try to break this apart. The way we're going to break down x squared minus 9, the way we're going to factor it is, that's difference of squares. Difference of squares factors into conjugates. X times itself gives you x squared. 3 times itself gives you 9. So therefore, there is your factored form. F of x is equal to this stuff now. Now that you have your factored form, your x-intercepts, your roots, your zeros, are x equals -2, -1, -3, and +3. Those are your zeros. Okay, number 10, your possible rational roots. All the factors of 6, which is 1, 2, 3, and 6 over all the factors of 2. And unfortunately, this time we have two different factors on bottom, so we do have to do the combinations. Everything over 1 to begin with, 1 over 1, 2 over 1, 3 over 1, 6 over 1. We know that that would be 1, 2, 3, and 6. Then we're done with that. All the factors over 2, we got 1 over 2, which would be plus and minus 1/2. 2 over 2, we've already listed. 3 over 2 would be positive negative 3/2. And then 6 over 2, we've already listed that one as well. So here are our possible rational roots. Now let's test them to see which ones work. And we really don't want to start testing fractions, so let's see if we can find a whole number that works. Let's start by testing maybe 2. Is 2 a factor, is 2 a root, which would mean that x minus 2 is a factor. There's your coefficients. 2, 4, -1, -2, -3, -6, and 0, and we actually got this one right off the bat. So what we've just did is we rewrote our original function. Let's come over here to the side and write it again, and let's break it down. My original function was 2x to the third minus 5x squared minus x plus 6. Since you took that function and you divided by x minus 2, you can now rewrite it into x minus 2 times whatever you had left over. Not the remainder, but the leftovers. Constant x squared. So that would be 2x squared minus x minus 3. And again, now we can use these new methods, but it's much quicker and easier to use old methods. This is slip and slide factoring. Change colors. That'd be x squared minus x minus 6. Factor like normal. X and x adds, multiplies, be a -3 and a +2. You slip the 2, so now let's divide by it. And that turns your new function into, bring down the x minus 2. X minus 3 halves does not reduce or divide, so move the 2 up. That'll be a 2x minus 3. X plus 2 over 2 would be x plus 1. So that's the factored form of your function. Everything is now linear fractions. So your zeros are x equals 2. Set it equal to 0. Move the 3 and 2 over. That'd be 3 halves and -1. That's your 3 intersection points. And again, if you think about this, x to the third graph, the general form, what does that actually look like? Would look something like this probably. Here's the x axis. It will have 3 intersection points, and there they are. Number 11, let's do another one. We're looking for 3 on this one as well. All the factors of 15, which is 1, 3, 5, and 15, over all the factors of 4, which is 1, 2, and 4. Every combination, first off, everything over 1 will be 1, 3, 5, and 15. This one's going to have several. Everything now over 2 will be plus and minus 1/2, 3 halves, 5 halves, and 15 halves. And then finally, everything over 4 will be plus and minus 1/4, 3/4, 5/4, and 15/4. So there is a long list of possible rational roots, and we don't like to see this. But let's pick one. That's all you can do, unless we'll try to stay away from the fractions first, and we will just pick one randomly. Let's try a +3 right here. So let's see if 3 is a root. At least we know that possibly 3 of these will work, so that's one perk. So you have dividing by x minus 3 to see if 3 is a root, or again, you're simply placing 3 into this function to see if you get 0. And the way we're doing that is by synthetic substitution here. Bring down the 4, and I don't think this is going to work already because there's no negatives. You'll see that? 33. So look what happens. This gets bigger and bigger and bigger. And you're not going to get, there's no way possible you're going to get, is that right? 398, yeah. There's no way possible you're going to get a 0 root when all these things are positive. So you scratch that and you try something different. So let's try negative 3. 4, 21, 32, and 15. So think about this. Since all of these are positive, if you ever use a positive number out here, you're bringing numbers down that are positive and multiplying by positive numbers. Again, it'll only get bigger and bigger and bigger. So that's something to look out for is, are all your coefficients positive? Because if so, your root's going to have to be negative. So let's try negative 3. Bring down the 4 gives you negative 12. That'd be 9, negative 27, 5, negative 15, and 0. So that worked great. So that means that this gives us, we plugged in negative 3 and got 0. F of negative 3 is 0, which means that x plus 3 is a factor. So let's rewrite our original function. And our new function is going to be, we divided by x plus 3, and we got this. 4x squared plus 9x plus 5. Now here's another thought. Since the original function did have 4 terms, you could have tried to factor by grouping there. I didn't point out that to begin with. It would not have worked, but you could have tried that to start with. We're now going to use slip and slide method here. Let's see, that turns into x squared plus 9x plus 20, which factors into x plus 4 and x plus 5. You slipped a 4. So my new factored form is going to be, bring down the x plus 3. X plus 4 over 4 will be x plus 1. And this does not reduce or divide, so bring the 4 back up, and that gives you 4x plus 5. So there's your factored form of your function. So your zeros are going to be x equals negative 3, negative 1, and negative 5/4. And you can look at your list. Negative 3, negative 1, and negative 5/4 were all on your list. Number 12, let's try again. Again, we're looking for 3 different zeros here. The possible rational roots are all the factors of 10, 1, 2, 5, and 10. At least we don't have as many here over all the factors of 3, which are 1 and 3. Every combination over 1 will be a 1, 2, 5, and 10. And then everything over 3 will be 1/3, 2/3, 5/3, and 10/3. So we still ended up with 16 different possibilities here. Let's try to find one that works. We will try a negative 2 to begin with. Our coefficients are 3, negative 8, negative 33, and negative 10. Bring down your 3, multiply, gives you negative 14, multiply gives you 28, that's a negative 5, which will give you 10, 0, that is a root. So therefore, we're going to break down our original function. And since we just divided by negative 2, that means that x plus 2 is a factor, and we got this, 3x squared minus 14x minus 5. Now again, we're going to use slip and slide method on this part. Let me change colors. So that's now x squared minus 14x minus 15. You get really good at factoring and synthetic division in this section. That's a negative 15 and a positive 1. We slip the number 3. So now let's divide by it. So our new function is now x plus 2. This is x minus 5. This does not reduce or divide, so that'd be 3x plus 1. So there's the factored form of your functions. So your zeros are negative 2, positive 5, and negative 1/3. Okay, number 13. Just got a couple more, I believe. 13, we're now looking for 4 roots. And I'm going to show you, I might show you a trick on this, and we'll do this one the other way. So 4 different roots, all the factors of 30 over all the factors of 1. That's going to be plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. Over all the factors of 1, which is just 1, and those combinations will give you just these numbers. So here's all your possible rational roots. So here we go. Let's see if we can find one that's going to work. Let's test negative 1. 1, 1, negative 31, negative 61, and negative 30 are our coefficients. 1, negative 1, 0, 0, negative 31, 30, 31. That'd be 30 here, negative, or that, hang on just a second. That should be a negative 30 there, which makes this a positive 30, which gives me a 0 here. So what you've done, you have now found one of your roots. You divided by x plus 1 to factor this function. So let's rewrite the function now. F of x is equal to x to the 4th plus x to the 3rd, this is your original, minus 31x to the 2nd, minus 61x minus 30. You divided by x plus 1, and you got this, which is x to the 3rd minus 31x minus 30. Now here's what I want you to do, because you don't know how to factor that. There's no other method. You've got to break it down again. But here's the thing. Don't try to break this down again. We're not breaking down the original function again. You're not looking for a list through this list right here to find something that will divide into this. Here is what you're now trying to break down. So what you can do, if you would like to, you can reevaluate this. You can do, okay, now let's take this constant term and this coefficient, find all the factors of 30 over all the factors of 1, and you might, sometimes you can shorten this list. In this case, it actually ended up being the exact same 2 numbers. So the list is not going to shorten, but you can reevaluate, see if that list will shorten. So now we're looking to break down this, which oddly enough is right here. So do not go back and break this down again, but we're going to break down our result. So now let's try to find one of these values that is now a factor of this so that we can break it down. I'm going to test negative 5. Let's see if negative 5 is a factor of, or excuse me, is a root of 1, 0, negative 31, negative 30. Bring down the 1, negative 5. Add those together, gives you 25. That's a negative 6, which gives you a positive 30, remainder of 0. So it does work. Let's rewrite the function. Bring down x plus 1. This stuff you now divided by x plus 5, and you got x squared minus 5x minus 6. Once you hit quadratic, now you can use old methods. X plus 1, x plus 5, 2 sets of parentheses, adds, multiplies, x minus 6, x plus 1. Therefore, your zeros of this function, and you can check the list, they're all there, are negative 1, negative 5, positive 6, and negative 1 again. So this one, if you remember correctly, has a multiplicity of 2, which again means it's a 0 twice, which means if you were to look at the graph of this at negative 1, remember, it would be tangent. If it has a multiplicity of an even, it would be tangent instead of crossing. Okay, last one. Again, we're looking for 4 different ones here. All the factors of 16 over all the factors of 1. That would be positive negative 1, 2, 4, 8, and 16 over all the factors of 1, which is just 1, so we're good with this list right here. So let's test them and see if we can find one that works. I'm going to test 2. My coefficients again are 1, negative 12, 28, negative 16. Bring it down, multiply, gives you a 1. Multiply gives you negative 10 when you add it, negative 20. That'd be a positive 8, 16, which is 0. So therefore, that is a factor. So you took your original function, and instead of writing the original again, I'm just going to write what it broke down into. You now have x minus 2 times this stuff, which is x to the third plus x to the second minus 10x plus 8. Now here's what I want to do. I want to take all the factors of 8 over all the factors of 1 because this is now what I'm trying to break down, not the original. So I'm going to take all the factors of 8 over all the factors of 1. Now, which one of these can I exclude because it's not all the factors of 8 over 1? 16 is not. That's not a factor of 8. Now, 1, 2, 4, and 8 does still fit that, but you can get rid of 16. It's not going to work. So as I try to reevaluate and see which ones work for this one, I can scratch that one. So now let's try to find another one that's going to work for our new function. It doesn't factor by grouping, by the way. That is an option. So I'm going to try maybe 4. Let's see if 4 is a root of our new function that we're breaking down. 1, 1, negative 10, and 8. Bring it down, multiply, gives you a 5. 4 times 5 is 20. Negative 10 and 20 is a positive 10. That's 40, 48, so that doesn't work. Now here's another option. Instead of rewriting that again, I would come down and make note of it somewhere. F of 4 was 48. So that way you wouldn't try that again. And you can now erase these, and you can try a new number here instead of rewriting that over again. So let's try maybe a 1 next. Bring it down, multiply, gives you a 2, multiply, gives you a negative 8 gives you a 0 remainder. So therefore f of 1 is 0. So now we broke it down again. Bring down x minus 2. You divided by x minus 1. And you got constant x squared. That would be x squared plus 2x minus 8. So your new function, x minus 2 times x minus 1 times, let's break it down old style. That'd be a positive 4 and a negative 2. So my zeros are x equals 2, 1, negative 4, and 2 again. So this one again has a multiplicity of 2. So there are your zeros.